This is the second video of our Chapter 34 dealing with energy density and spectrum for electromagnetic waves. Electromagnetic waves carry energy as they travel through space, and this energy can be transferred to objects placed in their path. The energy is shared equally by the electric field and the magnetic fields of the electromagnetic wave. For any electromagnetic wave, the total average energy per unit volume is given by U average is equal to 1/2 epsilon naught E max squared. And this is of the form of energy that we've seen in other devices, like if you said energy stored in a capacitor, you would say 1/2 C amplitude V squared, or energy stored in an inductor, 1/2 L amplitude I squared. This is the energy per volume in an electromagnetic wave given by the electric field vector. Or equivalently, we can write it as the energy density, energy per volume, is 1/2 1 over mu naught, the maximum B field squared. The units of this energy density is joules per cubic meter, energy per volume. The rate of flow of energy in an electromagnetic wave is described by the Poynting vector. And as a vector itself, it's equal to 1 over mu naught, the E field crossed with the magnetic field, electric field crossed with the magnetic field. If we did that cross product, looking at this diagram here, if you point in the direction of the first vector, the electric field, close your right hand in the direction of the second vector, the magnetic field, you have the resultant vector, the Poynting vector. And it actually is pointing in the direction of propagation of the wave. So in a sense, it points in the direction of its propagation, even though pointing is named after pointing and it's not named after pointing. But it works. The magnitude of the Poynting vector is actually power per area, or intensity, and is given by the magnitude of the Poynting vector average is intensity is equal to C times the energy density U. Or we could say that I is equal to CU, or ICU. That's one way to remember it. U average is the energy density in either the E field max form or the magnetic field max form. C is the speed of light, 3 times 10 to the 8 meters per second. So note that the units of this intensity, which is the speed of light times the energy density, should be meters per second times joules per cubic meter. 1 meters will cancel out. And this is equal to joules per second over meter squared. Now joule per second is a watt. So this is a watt per meter squared, power per area, which is indeed the units of intensity. So we can be confident that this is indeed giving us units of intensity in the SI system, metric system. Electromagnetic waves also exert pressure. We think of pressure in the purest sense as a force per area, but we can equivalently think of it as energy per volume, because force times distance is energy, and area times distance is volume. For complete absorption of energy, the pressure equals the energy density. So pressure is equal to the intensity divided by the speed of light, which in turn is equal to the energy density. That would be if you had complete absorption of the electromagnetic energy into your object. For complete reflection of energy, the pressure is equal to twice the energy density, 2 times the intensity over the speed of light, 2 times our energy density. It always happens when I have a reflective surface. Pressure units are newtons per meter squared, which we could write as Newton meters per meters cubed, or joules per meters cubed. So pressure has the same units as energy density. Energy per volume is the same as force per area in a sense. One way we could determine radiation pressure is to set up this configuration where we have a black disk, which is absorbing your radiation coming in. We have a mirror that is reflecting your radiation, thereby really giving you a double change in momentum. And where that comes up to an equilibrium point, you can measure those angles and determine from that what the difference in pressure is on either side and determine the radiation pressure from that. The electromagnetic spectrum. When we talk about electromagnetic waves, we're talking about orders and orders and orders of magnitude of frequency. As I look at this diagram here, we have gamma rays at 10 to the 20 in terms of hertz and frequency, all the way down to 10 to the 4. We could even go below that. And so we're basically 20 orders of magnitude for this whole electromagnetic spectrum. Visible light is just a thin band in that spectrum. It's really from the point of 400 nanometers to 700 nanometers, so it's not even one order of magnitude within this 20 orders of magnitude. And just that thin band is the visible light that we talk about all the time. So this electromagnetic spectrum involves radio, microwave, infrared, visible spectrum, ultraviolet, X-rays, gamma rays. They're all electromagnetic waves. There's no real sharp division between one kind of electromagnetic wave and the other. It's kind of a fuzzy as you go from one group to the next as far as division point. Here are some notes on the electromagnetic spectrum. Radio waves used in radio and television communication systems. The wavelength can be many meters in length. Microwaves have wavelengths about 1 millimeter to 30 centimeters, which involves the excitation range for water, so that's why it works so well in heating up water. Well suited for radar systems. And microwave ovens, radar ranges are application. So they do excite water molecule levels, which, water molecules are present in most food items, hence it works well for that. Discovered by Percy Spencer in 1946. Radar was really important in World War II. In fact, it was probably attributed as one of the things that helped win the war for the Allies. And so after the war, radar was being investigated further as to its possible applications, better applications for detecting things. So Percy Spencer was kind of involved in that, and one day he walked into a lab where they had these radar guns going, and he walked in, and in his pocket he had a candy bar, chocolate candy bar. And after a while of investigating and looking at these systems while they're running, he noticed that his chocolate bar had melted into a goo. And so this got him thinking, he had an idea. And from this idea, he developed, do you know what he developed? You guessed it. He developed Spencer's Nut Goodie. Yes, from then on, he asked people to carry chocolate bars into the lab so that they could turn it into this gooey mush that they could package and send out and make millions of dollars packaging this product called Spencer's Nut Goodies. And on the side, he invented the microwave oven, radar range. Actually, here's a Reader's Digest article published in 1958 on Percy Spencer and the radar range. Percy Spencer is the nosiest man I've ever known. One day, a dozen years ago, he was visiting a lab where magnetrons, the power tubes of radar sets, were being tested. Suddenly, he felt a peanut bar start to cook in his pocket. I think it was a chocolate bar. Other scientists had noticed this phenomena, but Spencer itched to know more about it. He sent a boy out for a package of popcorn. When he held it near a magnetron, popcorn exploded all over the lab. Next morning, he brought in a kettle, cut a hole in the side, and put an uncooked egg in the shell into the pot. Then he moved a magnetron against the hole and turned on the juice. A skeptical engineer peered over the top of the pot just in time to catch a face full of cooked egg. The reason? The yolk cooked faster than the outside, causing the egg to burst. So they're cooking all these things and not realizing they're probably cooking themselves at the same time. Spencer had discovered that you could cook with high frequency radio waves. He got a patent on the radar range, one of the 225 he holds. The new device will cook a sirloin steak in 1 minute, a plump Thanksgiving turkey in a little more than half an hour, used for some time in restaurants, Pullman diners, and ocean liners. Radar ranges are now being produced for the home. And so hence the microwave oven. More notes on the electromagnetic spectrum. Infrared waves, sometimes incorrectly called heat waves, produced by hot objects and molecules readily absorbed by most materials. Visible light, part of the spectrum detected by the human eye, but just that thin part of the electromagnetic spectrum. Most sensitive in the middle of that range at about 560 nanometers, which corresponds to yellow-green, which happens to be the color of a tennis ball. So tennis players got it right. And in fact, I even have glasses that help you focus just on that color so that you can see the tennis ball a little bit more easily. Ultraviolet light covers about from 400 nanometers to 0.6 nanometers. The sun is an important source of ultraviolet light. Most of the ultraviolet light from the sun is absorbed in our stratosphere by the ozone layer. In fact, the ozone layer absorbs 99% of the UV light incident on the Earth. 1% gets through, and that's what we complain about when we put our SPF on, is that 1% of UV light that makes it through the ozone layer. If the ozone layer gets depleted, and say 2% makes it through, the result on us is 100% more ultraviolet light at the Earth's surface. So we can see why the ozone layer would be important. X-rays. Most common source is the acceleration of high energy electrons striking a metal target. This is used as a diagnostic tool in medicine. In fact, X-rays were first discovered by accident in 1895 by William Röntgen. There's William Röntgen. And the first X-ray, very famous, was an X-ray of his wife's hand. Put his hand down, took an X-ray of it. You can see all the bone structure. You can even discern the wedding ring that she had neglected to take off. This made William Röntgen very famous, and he continued to study X-rays. In fact, it became very famous. He would have his friends over, they'd be, watching the game, downing a few brewskis, and then he said, honey, come in here. Guys want to see you do that X-ray thing again. And this happened over and over again. And when they realized over time that the X-ray kind of started to deteriorate. The first X-ray, very nice image. After 200 X-rays of plopping the hand down, taking the X-ray, found that some features of the X-ray had started to diminish. Very interesting. I hope I pulled that off. Gamma rays, emitted by radioactive nuclei, highly penetrating and can cause serious tissue damage. Looking at different portions of the spectrum can produce different information, and that's why, if we're looking out in the universe, you look at all the electromagnetic spectrum, not just the visible thin layer, but all the electromagnetic spectrum to pick up information of what's happening out there in the universe. Here's an example. Here's a very famous object out in the universe, and this is the way it looks due to radio waves. Here's the same object, and this is the way it looks looking at the infrared spectrum. The same object, looking at it using visible light. The same object as we look at the X-ray portion of the spectrum. And we can look at the near ultraviolet, the far ultraviolet, visible, X-ray. Combine all these electromagnetic information together. And here's a composite of that very famous object. Actually, this is a remnant of a supernova explosion that occurred in 1054 AD. Chinese astronomers recorded this event, and they said that it was so bright that the night sky was like daylight for about a month, and because of this supernova explosion. And then this is the remnant of that explosion. Do you know what this object is? Very famous. You might know it. I'm going to give you a second to guess. Well, it might not be obvious. I mean, it's got a real famous name. It might not be obvious from this composite picture, but if we use the highest resolution, maybe you can guess now. I don't know. It's hard to tell. I mean, it's called the Crab Nebula, but I'm not sure the highest resolution really displays that fact. That's what it is, the Crab Nebula. Doppler effect. We have a Doppler effect occurs for electromagnetic waves as well as what we might have known for sound. It differs from that from sound waves because sound waves, you need a medium. And so motion relative to the medium is most important for sound waves. And the speed of sound depends on its frame of reference. But for light waves, the medium plays no role since light waves do not require a medium for their propagation. And the speed of electromagnetic waves is the same in all coordinate systems, so that are not accelerating. So it's really the relative velocity of the source and the observer that's important. So here's the Doppler equation for electromagnetic waves. The observed frequency is equal to the actual frequency times 1 plus or minus the relative motion of the source and observer to the speed of electromagnetic waves, 3 times 10 to the 8 meters per second. So we have F prime is the observed frequency, F is the frequency actually emitted by the source, U is the relative speed between the source and the observer. This is only valid when this relative speed is much smaller compared to the speed of light. When they become more comparable, then you have to modify this equation relativistically, but you can modify it to an equation that works for that. In this equation, the top plus sign is used when the object and the source are moving toward each other, top for toward, and the bottom minus sign is used when the object and the source are backing away from each other, bottom for backing away. So top for toward, bottom for backing away. Here's an example of a spectrum that you might see. In the laboratory, you wouldn't know what the hydrogen spectrum looks like. So at 0 speed, you know what that spectrum should look like, and you get the lines of the hydrogen spectrum. So if you're looking out at a star and you see that same spectrum and you see that it's shifted in wavelength and hence in frequency, you can see which way it's shifted. If it's red, shifted towards the red, it is a receding star. That means it's moving away from you. And if it's blue shifted, that means it's blazing towards you. Blue shifted blazing, red shifted receding. You can actually measure the speed of that star by its change in wavelength over the wavelength at rest, that fraction, the change over the rest wavelength times the speed of light will give you the speed of that star. That concludes the second lecture of Chapter 34, dealing with electromagnetic waves and the electromagnetic spectrum. And try your hand at the problems in this chapter.